This is Lecture 9B for Calculus 2 with an example of an unstable equilibrium. Here's the equation for unlimited population growth. Get the pen. Population varies with time. So here we have the first derivative equals k times p. K is some positive constant. P is greater than or equal to 0 as well. This is an okay, let's look at what kind of equation it is. First, there's only one independent variable, so it's an ordinary differential equation. Oh, there should have been the word ordinary in here too. I'll put it in. So it's an ordinary differential equation because there's only one independent variable. Okay. The highest derivative is the first derivative. That makes it first order. Now the independent variable is t, but it does not appear explicitly. There's no, in this equation right here, there is no t. That makes it autonomous. And now the first derivative appears to first power only. The function itself, p of t, appears to first power only. It's a linear. It's linear. Okay, so it's autonomous, linear, first order, ordinary differential equation. So let's look through it just like we did for Newton's law of cooling. First, we want to find the values of p of t for which the first derivative is 0. These are our equilibrium solutions. So if we set the first derivative equal to 0, that will mean that Kp is equal to 0, means p is 0. Alright, the line p equals 0 is an equilibrium solution. This means that if the population starts at 0, it continues to be 0. Well, that makes some intuitive sense. Okay. Now let's look at nearby solution. So here was our, whoops, that wasn't our differential equation. It was dp by dt equals k times p, where k is greater than 0. Okay. So p equals 0 is your equilibrium solution. The only thing you can start off, because population also has to be greater than 0, is the case in which p is greater than the equilibrium solution. So if p is greater than 0, then the first derivative is positive. So dp by dt is going to be positive. We can take the second derivative, and this is what we get here. The second derivative is constant k. Remember, k is greater than 0, so actually the second derivative is always positive. Alright. The fact that the first derivative is positive means that the solution, the population, will be increasing. Because the second derivative is positive, that means that the lines are going to be concave upward. And in the next graph, I'll show you what that looks like. Alright, here is the equation. I'll write it out here in bigger letters. The first derivative of the population, that means the rate of change of population with respect to time, is k times p, where k is some positive constant. Right? The equilibrium solution is p equals 0. This is your equilibrium solution. Any solutions that start with a 0 population, right here, stay, let's draw that out a little harder. This is my equilibrium solution right here. If you start with 0 individuals, the population does not get either bigger or smaller. In fact, it stays at 0. That's my equilibrium, and that's what is noted right here. Okay, what happens if you start with a population greater than 0? Then the first derivative is positive, so the lines are going to start here. So you start at, I don't know, that's about 10. Okay, as time goes on, you get more and more people in your population, and the curve is concave upward. There's your solution right there. Here's the solution starting maybe at 20. This solution starts at 25. Doesn't matter if you start very close, like at 2. individuals, or maybe one if you have bacteria, this is what you get. The nearby solutions do not converge to that line of equilibrium like they did for Newton's law of cooling. Instead, they diverge away from the equilibrium solution. So this P equals 0 is an unstable equilibrium. Nearby solutions move away from it. They do not move towards it.